Hello, everyone, and welcome, PhD students from University School for Advanced Studies of ISS Pavia. Um, Welcome to my video. This video is going to be my first video ever that I'm going to upload to YouTube. In this video, I wanted to introduce work that I have done. Yeah, during my PhD thesis, which is still under development, but I believe it's quite stable at the moment. So I wanted to make a video about it because of the feedback that I received from some of my colleagues. They told me that it's going to be useful and maybe easy for some people to install and also for its usage. So I call this code EzGM. It is written in Python, mainly for the earthquake engineering field. And what it does is to select gram motion records based on the procedures which are in the state of art, but also based on the building codes. And also it can be used to process gram motion records and in an easy manner. That is its purpose basically. So there's a link here that you can find the codes, and I'm going to put this link in the description of the video. Basically, I created a repository for this code. You can find it online in this link. And what's the advantage of this code? Let me explain it a bit and what actually it does in detail. So the code has actually three modules, and these are selection module, which I described here on the GitHub page, utility module, and then there's a signal module, which I call. And the code is mainly used to select gram motion records, as I said before. And since it is written in Python, it can be used in any computer, anywhere else, and Python is open source, as you know, so there's no problem. Also, with regards to that, it's a sort of API that you can think of. So the selection module, as I said, is used to generate or select actually records based on condition spectrum or unconditioned spectrum. In the case of condition spectrum, it utilizes the spectral acceleration at a given period as an intensity measure, or it utilizes an average spectral acceleration for a given period array. And the tool makes use of OpenQuake hazard library, which is a very big library. It consists of a number of gram motion prediction equations, and the GM project, Global Earthquake Modeling Project team, they update this tool on a daily basis. It's pretty amazing library in my opinion. And if you have no idea about what's condition spectrum, it's quite interesting to learn, in my opinion, because it is very smart, and it was introduced by Professor Jack Baker from Stanford, I think in 2006, if I'm not sure. And he actually has a very nice video about it. I just strongly recommend you to go over it. If you write Introduction to the Conditional Mean Spectrum in YouTube, you'll see the explanation for it. But also, regardless, I recommend you guys to read the original paper about it. I mean, there are various papers that you have to read, in my opinion, before using such an approach for gram motion record selection. But still, if you have already idea about this concept, I think this tool is going to be handy for you. So while creating the module, I strongly inspired by the original code, which was created by Professor Jack Baker. He wrote this code in MATLAB, I believe, he and his colleagues. I think there's the other contributor, Lee. And at the moment, actually, they are able to select gram motion records, considering the 3 components, 2 horizontal and 1 vertical component. And although this is a great improvement, I do not know still if many people are utilizing the vertical components or not, but I think it's pretty important. There are many various studies that show that the vertical component has a significant influence in the structural response of the buildings and maybe some certain type of buildings. And yeah, you can access this code from his own repository. So I inspired quite a lot of things from this code. But main problem is it's written in MATLAB, and the code itself has only few gram motion prediction equations where you can utilize. And another thing is you cannot directly download the records upon selecting them using this code. So it's just going to give you the name of the gram motion records that you need to download basically. In my opinion, this is not very practical. So I just wanted to do something about this as well while creating my code. And since it's MATLAB, it's not open source, right? That is another problem. And it has only one gram motion database inside here. I mean the real gram motion database, which is the NGWest 2 and NGWest project, and then there are a bunch of simulated gram motion databases. Yeah, so this is basically what this code does. In EzGM case, I have introduced usage of also the European database, which is created in 2018. So, and then there is the NGOS2 database. And I also found which records do not exist in the database, or they're not accessible. I don't know actually if they're still there or not, but I know that they are not accessible by users. So I just discarded these records from the flat files or from the databases, and I just created my own metadata file, and you can actually access those here from here. So these are the two mat files that you have, and there is this CSV file which I use for creating the design spectrum, elastic design spectrum for the Turkish building codes, because I needed to base the hazard information related to each longitude and latitude in Turkey. So let's go back. Yeah. So you can keep, if you want, upon having the source code, you can add your own database if you have some other database. For example, I have used another database which was the simulated gram motion database by ExIM for a study that I have carried out. And then EzGM, actually, I forgot to mention, allows you to download the records upon selecting directly. Only thing you need to do is having credentials from the related websites for NGOS, for example. For NGOS2, you have to get the credentials from here, from here. And for European database, again, you need to have the credentials from here. I give you the links already. So if you have those, and you'll be able to actually download the records and have them ready to use in the structural analysis. The software is going to download them and process them and put in a format such that acceleration values are provided in a single column inside a TXT file. And you're going to have in a separate file all the time steps related to each gram motion record. So it's going to be ready to use for structural analysis. Okay, that is the main idea of the code. Then the second module, utility module, can be used to do some post-processing of the probabilistic seismic hazard results from OpenQuake engine. Actually, I use this for my seismic hazard analysis, and then for my disaggregation. And then I use the results to select my records using the condition spectrum approach. And you can visualize basically using the tools inside. I think that's a great option to do. So there are other functions that you can use that I'm going to show maybe in one of the notebooks. But the main functions, I believe, are these, which can be used to post-process PSHA results. But for example, there are some functions where you can create, I don't know, elastic design spectrum for a certain code, or you can convert, for example, GMP logic tree of an OpenQuake hazard model from SAT to average SA and vice versa. Then there is a signal module, and this module can be used to process ground motion records in a way that you will obtain, for example, different intensity measures such as auxiliary intensity, significant duration, spectral acceleration, I don't know, input energy, etc. And moreover, you can do the filtering of the records and baseline correction. You can apply baseline correction on the records. And this is mainly used for these purposes, the signal module. And at the moment, I don't have documentation for the EzGM because I actually didn't have time to do so. And it will take some time for me to do it, and it depends on actually feedback that I received from the community or from my colleagues. If they think that's going to be useful, it worth my time, I'm going to do that. But at the moment, I don't have such time, and I'm still developing the tool. There are certain potential improvements that I want to do in the future, such as adding the 3-component selection. At the moment, I can only select 2 components at most. Addition of spectral matching methods. This is still something I want to do, aside from the code-based selection and condition spectrum-based selection, addition of the generalized condition intensity measure approach, and maybe some alternative code-based ground motion selection procedures. But yeah, these are the future developments that I'm aiming for. Also, the computation of the exact condition spectrum, because at the moment the code only computes approximate condition spectrum. It doesn't allow you to compute exact condition spectrum. So last thing I want to mention before proceeding, you can use the codes within an online service such as Binder, which is an interactive computational environment for online GitHub repositories. And you can also use Google Collaboratory. It is also an open source free service which is provided by Google. So if you click on these links, you are going to see my examples, some of the examples that I have provided for the code. For example, this is the binder one. It's going to direct you somewhere like this, where you are going to see my notebooks that I have placed in GitHub. And for example, you can scroll, go to the examples folder, and you can see that this binder folder has these Jupyter notebooks. So you are going to see them here if you click on the binder button. And then there's a Google Collaboratory, but you can see some of the same notebooks here as well. If you go and open those in the Google Collaboratory, for example. So I have provided basically a simple tutorial which explains how to use this and etc. You can go and check, but I'm going to provide the explanation for these just in a moment. And then in this example file, you have actually the Python scripts itself instead of the notebooks. We are going to look at how to use them as well. And then these are some input files that I used in my examples. So if you want, you can also go and look at them. So there's an OpenQuake hazard model, seismic hazard model. There's a target spectrum that you want to use, for example, if you want to select your course based on codes and building codes. And there's a records. There's a earthquake ground motion record, for example, three components of it. If we are going to process these records with the signal module that we have. That is the main idea. And yeah, let's continue. Let's start with the installation. Actually, one thing I want to explain in the very beginning. Let's close these. Okay, for now. So if you are going to install this software into your own computer instead of using these online service providers such as Binder or Google Colab, I always use it in my computer instead of these, but I know that it can be handy if you do not want to deal with all the installation procedures, blah blah, because it's going to be easier to just launch everything from Binder, for example, because all the things are basically ready for you there. You do not need to install anything. You just need to, I don't know, have browser somewhere that you can open the Binder, and that's it. You can even access this using your phone or whatever. Okay, but if you want to, let's say, install it into your own computer, there are a few requirements that we need to follow. So one is that, if, for example, if one is the dolnut module, ngos2 dolnut method. I'm sorry, not the module, because it's a function inside a class. So basically, this method is used to download records from ngos2 database upon performing the ground motion selection. And for that, we need to have Google Chrome installed and Firefox installed in our computer, because basically we are going to use one of these two browsers to go to the website and get the records. At least this is what code does automatically. So you need to have them ready, even though you're not going to use them explicitly. But I imagine most of the people have either one of them. At least I know that Linux users generally tend to use Firefox, and Windows users generally tend to have Google Chrome in their computer. I do not know about macOS. I'm sorry, I'm not a macOS user. Then the package requires several other packages, but you do not need to worry about them because they will be installed directly when we do the installation procedure. So you can either use the package management system pip to install directly the EzGM from PyP, because if you write PyP EzGM, you can see that it is already installed in the pyp.org, this project, and you can directly install it from here. Okay, so I created this package installable from online services. But I do not like this kind of installation because of the fact that some things are not very well installed when you try to install OpenQuake engine, which EzGM uses. Especially in Windows, this type of installation may cause some issues, some dependency issues. So I do not favor this too much. I recommend not to use this if it is possible, at least in Windows, not in other um, other type of platforms. I think in Linux there's no problem. You can directly use this. And also the fact that I do not always update PyP, and because of the time or etc. Sometimes I just push some stuff here and I forget updating this from PyP. So I do not like this approach too much, but yeah, as I said, you can still use it. For example, binder directly installs EzGM using pip install EzGM. Okay. Then, if you do not want to use this, the other approach is going to be just basically about cloning the source code into your computer and then installing it into your computer basically from the source code, right? This is the other approach that I usually follow. Okay, so for this purpose, I'm going to recommend you guys, first of all, to use Anaconda in your computer if you are gonna work with Python and different environments. I think it's pretty handy. I myself always use Anaconda Navigator. Okay, actually not Anaconda Navigator, but Anaconda itself. This is just a user interface, what they call Anaconda Navigator. So if you go and if you go and Google it, you can find a link to download it. Okay, for Windows, but also for other platforms, they have installation. Okay, I I really like this one. It is an open source tool, and it is very user friendly to install packages and switch between environments. Okay, because otherwise, I don't know, you need to do things separately and etc. I don't know, especially in Windows, I think Anaconda solves many problems. It's pretty useful. So this is the first thing to do. So download this and install Anaconda, okay? But it's up to you again, as I said. So when you install it, if you open Anaconda Navigator, okay, this is Anaconda Navigator, you will see something like this, okay? If you are not a Python user, this can be a little bit different for you because if you're a MATLAB user, everything is already built in. You do not need to install any libraries. You have a beautiful IDE and etc. But in the case of Python, you need to install things separately. That is why it's not heavy. Okay, there's something called, for example, like Spider, which is like something like MATLAB IDE. Okay, you can use this initially in your work. Okay, it's going to be pretty easy. When you have this, I would like you guys to go to the environment section and create a clean environment. Okay, this environment can be 3.8 or Python version can be using Python version 3.8 or Python version 3.9. Okay, let's select, for example, 3.8. Okay, I'm going to name my environment as my environment, my M. Okay, so I'm going to create a new environment where I am going to install EzGM. I already had another environment for my work, what I call EQEng or Earthquake Engineering. You can say I use this usually for my work, but let's see the installation for this. So I have my environment ready, okay, right? It's called my env, okay, my environment. So we are going to install everything basically to this environment, this Python environment. So first thing, if you go and read the README file, says that first create a clean environment with Python version greater than 3.7. Okay, also lower than 3.10, but I forgot to write it here actually. So be careful with that. I think it doesn't work well with 3.10, but anyways. Then it says that upgrade the pip package management system that we have. So for that, go open the terminal using this environment, then copy paste the thing. Okay, I already have it upgraded in my computer, so it doesn't do it again. I think it depends on the base environment that you have. If it's already upgraded there, you do not need to upgrade it on the other environments. That's what I think. So we have the pip already upgrades, right? This pip upgrade is important because maybe you will have some issues while installing some packages. It may cause some dependency issues if it is outdated, right? That's why I want to have it with the latest version. Then it says go to the OpenQuake engine repository to the source code and clone it. Then go to the directory here, open the terminal inside the clone directory, then activate the environment you want to install the package, then install the package using this command here. Okay, this is the one we have. You can clone it directly by download link, or you can use a GitHub desktop application or Git application directly. For Git application, you may find several tutorials in the YouTube, but I find GitHub desktop application very easy, especially in the case of Windows. So if you write GitHub desktop in the Google, you can find it easily, right? This is the application installation. Okay, so I have it already inside my computer. The good thing about this is you can keep track of the changes happening inside any repository that you have cloned. For example, let's go to the OpenQuake engine source code. Let's check if there's any change. Let's check in. Apparently there are some changes. We can pull this origin and we can have the most recent version of the OpenQuake engine. Okay, this is based on the changes that developers make. Okay, so we are going to use this developer version in our code, basically, in our installation. Basically. So to clone it, as I said, although I already have it, you come here, you select file, clone repository, you come to URL, copy paste the URL. Okay. So we do this for both OpenQuake engine and also EzGM, and we have them cloned already in our computer. So it is the folder where I have the clones from my GitHub. For example, this is the EzGM directory, and this is the OpenQuake engine directory, right? So we have done the cloning part, right? This is what it says, clone OpenQuake engine source code. And now we are going to open a terminal inside the clone directory. If you would like to open the terminal inside the directory, you can have the shortcut here with some trick like this. I'm not going to show how to do this, but I believe you can find it. If you do not have it, you need to open the Anaconda prompt separately, then change the directory to this, basically, right? Now you are here. Then you have to activate the environment that you want to install EzGM. For this, you write activate my environment, right? This was the name of the environment. Now we are not in the base environment, but we are inside my environment, my env, right? Now we are going to copy paste the command that we have here, and we are going to install the OpenQuake engine into our computer. Okay, this may take a while if you do not have these packages already downloaded in your computer. It doesn't take too much time in my case because I probably already have downloaded them before and I already have them inside my computer. So basically, it downloads all packages OpenQuake engine uses and then it installs them into our environment. Okay, this is what's going to happen. And apart from that, as I said, you can still use this online service providers. Okay, and if you are going to do so, in the case of Binder, you do not need to install anything, and it's going to be ready for you to use all the environment. In the case of Google Colab, you need to do some tricks. For example, if you are going to work from your Google Drive, which I usually do, you have to mount it and you have to change the directory to where you find the notebook that you want to work with. Then you can install the basically EzGM and OpenQuake engine the same way we are going to do right now. Okay, so OpenQuake engine is installed in the end. You see this, right? Now we are going to do the same. we'll go to the EzGM directory, we'll repeat the command, and now we are going to install EzGM, right? Now we are going to have EzGM ready, right? Since most of the things are already downloaded, this is also fast. As I said, it's not going to take too much time. So there are several things that I want you guys to know. If there's any issue, as in the case of any projects, it is going to be under the issues section in GitHub repository, right? At the moment, there are maybe a few things that I would like to note. One of them is if you are going to use this environment and if your matplotlib is greater than 3.1.2, some plots, some subplots might have very wide white spaces, significant white spaces between them, and this is a bug that I couldn't solve. I mean, it's related to matplotlib, so maybe some of the plots that they will not look very nice when you do the post-processing. So you may want to lower the version down to 3.1.2 matplotlib version if you can. And the second one is related to H5PY package, which OpenQuake engine uses. If you run a PSHA, I don't know, several weeks ago, with this version of the package in Windows, I was having trouble. It was not working in the desegregation part, I think, when it tries to save the results, PSHA results. So if you are working in Windows and if you want to run a PSHA, I recommend you guys to lower this version to 3.1.0, right? You can just use this to lower it to down. And last thing is the package uses Selenium library. Selenium library is mainly used to download records from NGRS2 database using the ng download methods. So to be able to use this, please keep Selenium version fixed to the 4.2.0 for greater versions. I realized that they depreciated some of the functions which I use inside my codes. So until I change those, please don't use the version greater than 4.2.0. Don't use 4.3.0, for example. Okay. And I guess that's all about the issues at the moment. If there are any more issues, you guys can, of course, feel free to write there so I can try to fix them, or we can actually do something together. Okay. So EzGM is also installed, right? I'm also going to reduce the version of H5PY package, okay? And okay. So now everything is ready. For example, if you write Python, we have the Python 3.8 version. We can also import EzGM, right? Everything is ready. And my environment is going to use directly the directories which are here, okay? EzGM directory, this one. And then OpenQuake directory, this one. Okay, we are going to have all the modules here, okay? Now, let's go back and try to a bit explore what do we have in tutorial or example notebooks. Okay. Maybe one more thing before we proceed. Actually, I told you guys that you may also consider using Spider. Okay. If you would like to use Spider in your computer for applications, for example, if you guys want to use scripts I have and change those, but you also want to see the variables and etc. You want to have some idea. You can install this one. Okay. If you install this one, you'll have something like MATLAB. Okay, if you're familiar with MATLAB. I started using Python with this. It made things much easier in the beginning, so I believe it's going to be the same for you. That is That's why I'm recommending you guys, if you want to use something matplotlike, okay, this is going to be the tool for you guys. So I'm going to just show you how to open this. Right now it is just installing Spider into our new environment. Let it be installed. Once it finishes, I'm going to just open it, okay? But while it installs, I'm going to look at the tutorial that I have, okay? So let's talk about let's talk about the tutorial notebook that I have prepared for you guys. As I said, EzGM does not have any documentation, right? But instead, what I did was, not only for myself but also for you, I just wrote underneath each function uh, the description of the parameters or the use of each function. Okay, like it says, for example, let's go to one of the functions. Okay, this is the condition spectrum. Okay, uh, class that I have inside the selection module. Okay, and it is a function called create. Okay, this create function looks like this. Okay, this is excluding the self because self is related to the object itself. You do not need to have any entry for this. If you have created the object before, you will understand what do I mean by objects. If you know a bit Python, so I recommend you guys to have a look at basics of Python. Basically, these are going to be the variables that you are going to use, and if there's a value next to it with an equal sign symbol, it means that there's a default value that is assigned to this variable. Okay, so you can see what does a function look like, what parameters it takes, and what is the description for this function. It says create target spectrum, condition or a condition spectrum, basically. And this is the notes. Okay, it says that look at this one to understand what is OpenQuake hazard library, what are the different GMPs. Okay, and in order to check the required input parameters for each ground motion prediction equation, you can see this one, and these parameters are rupture parameters, site parameters, and distance parameters. Okay, then some of these parameters can be calculated by default by the software. Okay, and some of them actually are not described inside this documentation because these are basically used to calculate or derive some ground motion models parameters in accordance with Kaklamanos et al. 2011. Okay, within condition spectrum set context methods. These are not so important. Okay, you do not need to worry about it. What I mean is that if you did not define a certain parameter, let's say a div value, is going to be computed by the software automatically, but there are going to be some mandatory parameters which you need to define. Okay, and these are actually written here inside, and the documentation requires rupture parameters, depth, magnitude, rake, width, z-tor, site parameters, vs30, vs30 measured, uh, z1, pt, 0, and etc. Okay, this is what I mean. You have to have these parameters, but some of these parameters can be calculated automatically using the relationships given in Kaklamanos et al. Okay, if I am not mistaken, you need to have at least RGB rake magnitude, and what I mean by RGB is the joiner bool distance, rake magnitude, and soil vs30. The rest of the parameters can be computed automatically by the relationships given here. Okay, but otherwise you can also define them by yourself. And And then there is the references that you can look at if you are going to use this function. Okay, the base of this function is are these references. I forgot to write the Kakmanos et al. 2011, but you can find it, I'm sure, in the literature if you Google it. Then there's a parameters description for each parameter. Okay, this is going to be very, very long, but if you understand what is the concept behind condition spectrum, you can understand what each parameter means. Okay, T star, for example, is the conditional period. It's written here in case of FGSA, it's an array, it's not period. Okay, so based on what you want to do, you have different type of parameters, of course, and it is written here. And there's GMP, which is the GMP model, okay, from the OpenQuake hazard library. Basically this, Abrahamson 2014, for example. You can pick whatever you want from here, from this list, and use it, okay. And then, for example, there's the selection type. It can be single component, two components. There's the type of spectral acceleration definition. This is important in the case of two-component selection. Or depending on GMP you're using, you may use geometric mean, RT50 or RT100, okay? Then you have the site parameters. All the site parameters that you can use are defined here, okay? Among them, BS30 is the mandatory one. Others are not mandatory. They can be computed. Okay, it's required by all GMM. Same goes for rupture parameters. It's required by all GMM. Required by all GMM. Rate and magnitude. Rest can be computed. They're optional. Okay. Then there are the distance parameters. Again, at least one of these distance parameters are mandatory. Rest can be automatically computed if I'm not mistaken. Okay, and you have to check which one is mandatory from. At least which one you should use from here. Okay, from the required distance parameters. You can compute. You can enter a value for each of them, but at least there should be one of them. Then there's H-cont or H-contributes. This basically defines a hazard contribution for consider different scenarios. While creating condition spectrum, the approximate one, you may define several scenarios. For example, the default one has two different scenarios, okay, because this is a list. There's a list for rake, okay, as a rupture parameter. The first scenario has 0 rake, the second scenario has 45 degrees. The magnitude of the first scenario is 7.2, magnitude of the second scenario is 6.5, distance of the first scenario is 20, distance of the second scenario is 5. Then you can assign different contribution to hazard contribution to this different scenarios, okay? These can be somehow inferred from the seismic disaggregation, okay? But I tend not to use this approach, and I just compute the mean values if there are no obvious scenarios from disaggregation. And usually if one scenario always governs, or they have equal weights, many scenarios have very equal weights and the parameters they have are very close, I tend to just pick the mean value, okay? And then there's a period target range. Basically, this is the period range for our condition spectrum, okay? You can basically define a target and match your gram motion records within this range in terms of variability and in terms of mean. Then there's IMT star. This refers to the intensity measure level that you want to condition your condition spectrum. Okay, so not only the period, but there's also intensity measure level. And then there's epsilon. So you can either use epsilon. If you use epsilon, your intensity measure level will be median plus epsilon times standard deviation. Okay, if you do not use epsilon, your intensity measure level for the conditioning intensity measure level will be IMT star. Okay, then you may select, you may use conditional, or you may run condition or unconditional selection. Okay, this count parameter just for this. Then you can also try to match the variability in the condition spectrum, or you can just neglect the variance in the and then try to match the condition mean spectrum only. And then the ground motion selection procedure will change based on this. Then there's the correlation function that you would like to use while creating the condition spectrum. This can be Baker and Jaram or Akkar, okay? And it's just up to you. At the moment, there are only 2 correlation functions that I have implemented, but maybe in the future we will have more, or we will be able to compute the exact condition spectrum using the OpenQuake engine. Okay, so you can continue and check this tutorial notebook. Okay, I'm not going to read them aloud because it's kind of boring and I'm aware of them. I will just go through the example notebooks instead of them, so you will see their applications. Okay, meanwhile, I think Spider is installed, so let me just show you what does Spider look like in case you have no idea about it, because I know that at least some of my friends, some of my colleagues, they have never used Python before, so they have no idea about it, and they have used MATLAB before, so maybe it's going to be useful for them. Okay, so now this is actually the Spider, as you see, and this is the editor, Spider editor. You have things, and this is the console. Then you have the variable explorer or the workspace. You have help here. You can see the plots, visualize them. You can see in which folder you are working on, and etc. Okay, for example, if you run this code, you have some example here. This is the plot this script produces, and these are the variables that we are going to have upon running the script. Okay, for example, L1 is here, etc. So if you want to go and use the examples that I have, you have to go to the on directory, go to the demo scripts, and open one of these. Okay, and you have my examples, and you can start using this and play with it. But now I'm not going to show these examples on Spider, but instead we'll go and use Jupyter Notebook, okay, which is more humanly interactive environment to read Python codes and also use the Python. And I want to show this on actually Binder, not in my own computer, okay? So if you click on this link, this button, they are going to be directed into the binder, right? I was reading the tutorial notebook from here, right? Okay. So let's see. When you have this link, you can start with these examples. I already ran these examples, so I'm going to show what each example does, and also what do they give you as an output. Okay, so if we go to example 1, don't restart. Okay, I don't want to restart it. So the title of it is the condition spectrum based code selection. Okay, and I divided this into 3 parts. One part is the selection using NGOS2 ground motion database and intensity measure as an intensity measure spectral acceleration at a given period and using a single scenario. Okay, And then the part B is going to be the same, using European database for record selection. Only difference is going to be the rest is going to be same. And the third one is going to be the same as the first one, but it's going to use the as an intensity measure average SA. By the way, I said 3, but apparently I have 3. I name again the third one as part B. Okay, this actually needs to be C, but anyways, it's not important. You understand what I meant, hopefully. So let's see. So in the beginning of this example, I import several functions and a class that I would like to use. I import the condition spectrum class from selection module, and I would like to import from utility check GMP attributes, get ESM token, and runtime functions. Then I also import some other functions which can be handy, okay, for our needs, such as NumPy, which is a typical scientific library used in Python. And for time, I just want to import the time to compute the time which is passed while running all the code, okay? So I already run the code. I'm not going to rerun them, but you can use this button to run all of them. Or you can run all of them with this cell. You can restart the kernel and run them again, and you can clear the output and vice versa. Okay, you can add several cells if you like. You can go back to the folder and etc. Okay, at the moment it didn't open. I don't know why. Most probably it's disconnected. That is why. But I know that this is what you're going to obtain in the end. So this should be there. Oops, it is apparently not there. Oof, that is bad. That is very sad. So we need to run some stuff again. Okay, this is very sad. Anyways, let's go. Let's open it once more. Okay, this is going to be fine. But anyways, let's go back to the example. It doesn't change the fact that we have already run the stuff and we have this notebook. So in this notebook, what it does, I just start with initializing the object condition spectrum object. And if you go to the tutorial one and see what initialization object needs, what parameters it requires, and what do each parameter mean, you can read this. Okay, there's a parameter called database, and there's a parameter called outer, and their explanations are given here. This is the database, and this is the outer. I think I need to fix the format here, and this parameter is no longer here because I think I removed it. But anyways, the explanation is the same for these two. Okay. So we have picked the data as a database in JOS2, and we have defined our output directory folder. We named it as outputs A. Okay. And then we initialize our object. I call it CS. Then I wanted to first, before proceeding, check the attributes of the GMP that I would like to use from OpenQuake Hazard Library. If you use this function, we are going to see several things. It just says the name of GMP. It is defined for which region, what kind of standard deviation it has, what kind of intensity measures it supports. Average SA is explicitly defined. You'll never see it here in the supported intensity measures, but because we compute it separately. Then you can see the component intensity measure component type, which is geometric mean, for example. And you have the supported period range for this ground motion prediction equation. So you cannot define period range outside this range. Example, this referring to this parameter. Okay, you have to use something. Something is inside this range. Okay. Then it says require the distance parameter for this GMP. One of it RGB and rupture parameters, rake and magnitude, and then site parameters is VSGM. You at least need to have these parameters defined. Okay. That is what GMP says if you check the attributes. Then we are going to create a target spectrum using the create function. So we have already the object initialized. We are going to use the create function to create our target spectrum. And here we define some options that I have just described. Some of site parameter, as I only defined VS30. As rupture parameter, I only defined rake and magnitude. And I have one scenario, so I have a list with a single value, and for site parameter, it's going to be same regardless of the scenario, so you don't need to provide any list for the site parameters. And the same way for the distance, we have only a single scenario, and our distance RGB is 10 kilometers. So I do not need to define any hazard contribution. By the way, if you don't define, if you have more than one scenario, it's going to think that contribution is the same for both. Then my period range is 0.1 and 4.0. I condition my condition spectra to 1G. I do not define epsilon. I am using condition spectrum for my selection. I'm considering also the variance. I'm using ACCAR as a correlation function. Okay, these are the settings that I have. Then I can plot my target spectrum, okay, because I already created it. So I can use CSplot. You're going to just check. You can check what input parameters again you require by writing help or by just going here, find the plot. It just says that what each of these parameters mean. So I want to show the target spectrum, and then I want to save it. So I just put a 1 for its flag, and I want to save it. So I just set save equal to 1. I also want to show it. I set it to 1 again. Okay, this is the idea. So here's our target spectrum. It is conditioned on 1G, as you see, at period of 0.5. Okay, and this is the basically the variance two times the standard deviation. I'm sorry, and minus and plus from the mean. Okay, you can see what each the label for each line that you have here. Then the next step, sorry, is to select the ground motions. Okay, again, you can go to the tutorial and select what are the options for this function, okay, or you can just write help on your own to see what it means, right? So basically there are some parameters that we need to set. Okay, one of them is number of ground motions that we want to pick. We should define if the ground motions are going to be scaled or not. I say yes, they're going to be scaled to match the target spectrum. What is going to be the maximum scale factor that I would like to apply? It can be, it is going to be 4, and the minimum value is going to be 0.25 in this case because it's 1 over max scale. Then do I want to put some limitations on the magnitude of the ground motions? These are the lower bounds and upper bounds. Do I want to have some limitations on the VS30 of those? Do I want to have some limitations on the Joyner-Boer distance of those? And do I want to just choose ground motions with certain type of falls? Okay, I just need to set these here. and you can just see, for example, if you want to also limit the faults, you have to write, you have to check this. Okay, for NGOS2 database, the type of faults that you want to use are different also than ESM 2018 database. Okay, you just need to put, if you want to limit, if you have a limitation, you just need to define inside the list which type of faults you allow. Okay, which type of faults you want to choose for your ground motions for when you perform the ground motion selection. Okay, then there are some parameters which are not so important. This is basically setting of the grid optimization. Okay, you can increase the number of trials that you want to optimize your ground motion selection. You can give different ways to definition of your error. For example, you can have weight of 1 on your mean, error on your mean, matching of error on your mean, for example. This is the matching, okay? You give weight of 1 to the matching of mean. Then you can give weight of 2 to the matching of standard deviation. Then you can give weight of 0.3 to the skewness of this distribution, and also the distribution of the target spectrum, or the condition spectrum. Okay. So using these weights, both distributions, the spectrum of selected ground motions, but also the condition spectrum is uh, going to be undefined. Okay. So you can also play with the seed value to change your initial ground motion set while performing the ground motion selection. You can increase the number of loops that you want to perform while running grid optimization, and etc. So these parameters are basically not so important. Okay, you can also set penalty uh, to eliminate some of the ground motions which are not very well matching, but satisfies the distribution. So you can eliminate these with higher penalty factors. Okay, for example, you may have a ground motion which is going somewhere like this, although it helps you to satisfy your distribution, error on your distribution, minimize error on your distribution. It may not be so representative. Okay, it can be an outlier, large outlier, so you want to eliminate it. Okay. And then at this stage, we can also plot, as I said, I already saw the plots. You can plot the records that you have selected, and you can also plot the simulated spectra which are used for initial ground motion record selection. Okay, this is not so important in the end. In the end, what we want to see is this one, right? How the selected records, spectra selected records look like. Then upon finishing this, if you have used NGOS2 database for your selection, you can download the records from NGOS2 website. Okay, if you have credentials ready, if you have Firefox or Google Chrome, you can change this to Google Chrome. Okay, like this. You enter your password, you enter your username, then you can download all the records. Okay, here you see all the things which are going to happen during download. Okay, so when the download process has finished, you are going to have zip file where your records are basically located. Then I'm going to use the write method to get these records from the zip file and scale them and put them in a format such a way that um, all the records are provided in single column. Let me show you an example if I can. I think I have, let me see. Yeah, yeah, I think I might have something here. Oh, not here. Not here. Let me go to my PhD works. Okay. Maybe I have it somewhere. I have it here. Yes. Yes. Let's say we have performed gram motion selection. Okay. Then you are going to have something like this. Okay. You are going to have uh, when you write them into the files, we are going to have a file which is named as gmrdts.txt. Okay, these are going to be the time steps of your records. Okay, the selected records. Then gmr underscore h1 underscore names.txt. This is going to include the uh, first horizontal component of the selected gram motions if it is a two-component gram motion selection. Okay, these are the names of those records in an order. Okay, and again in an order the second names for the second component, and then you are going to have all the records ready in a single column, and the units of these records are going to be in G. Okay. So this is going to be a sort of output you will get upon running this write method. Okay. And if you would like to save the condition spectrum object that you have, you can also set the flag to 1 and you can save the object like this. Okay. Like the one here. And if you have the records already inside your computer, if you have, for example, some other gram motion database that you would like to use, you may have the records inside your computer in a zipped folder, and you can basically use those zip folders to get the records from. I think I have some of them already here. Yeah, I think I have some of them. Okay. I just have, for example, EzGM. Okay, I can get all the records from EzGM. Okay, if I implement inside the Google, inside the software, or it goes for ESM and etc. So let's continue, and this is going to be finished upon doing this as well. And in total, as you see, it took 1 minute and 20 seconds, which is quite fast in my opinion. And if instead if you want to use European Stored Gram Motion Database 2018, first you need to get the token uh, to download the records. So for this, you need to use get ESM token. If you have credentials already ready, as I showed you before, oops, I think I closed EzGM, so let's go back. If you already have them ready, which you get from this website in the link, you can just download the token directly with your credentials. Okay, this is the first thing to do. Then, as I said, we initialize our object using ESM 2018. This time, we do the same things for creating the target spectrum, also for plotting and etc. For selection, it's going to be the same, blah blah. Only difference is here that in this database, I think period values in the flat file are wider. The distance between them are wider, so it is less dense, and that's why you see more straight lines compared to the previous one. Okay, that is my one difference. Then you are going to use this time ESM 2018 underscore download method to download the records. Okay. Again, we are going to have the records in a zip file when we download them. And we are going to use the write method in the same way that we did for the previous one, and to obtain the records in a formatted manner. Okay. So that we can use for our structural analysis. Again, it actually is faster in this time, as you see. So It's quite fast. It took only 43 seconds to do all of this. Then if we continue, the third example is about you doing the same stuff, but this time using average SA instead of SAT as an intensity measure. Only difference is going to be the definition of T star. Here we are going to define an array instead of a float, okay? Here we have period values which are starting from 0.2. They continue until 2.2 with a with a with a distance of 0.2. Okay, it ends at 2.2. The last period is 2.2 because this function does not consider the last value. Okay, so it's going to always be smaller than this one. And if you look at the target period and the conditioning intensity measure, you are going to see that average SA, the period range for calculation of average SA is the shaded area, 0.2 and between 0.2 and 2.2, right? And our intensity measure is going to be a geometric mean of these spectral acceleration values. Okay, considering this array, of course. Okay, so let's say we are going to compute spectral acceleration at 0.2, 0.4, 0.6, blah blah, and we'll compute the geometric mean of those. Okay, that is the idea. Then the rest is going to be the same as we did before. First, we are going to simulate a bunch of spectra. Then we will try to match those simulated spectra based on to select our initial set. Then we will run the greedy optimization, okay, so that our selection will be quite good, okay. And you see this is the end result. And then we can again the same way run the records using one of the methods, using another browser, for example, and then write them into the formatted files, and then compute the time spent. So it's quite small again. Okay, that's the first example. If you continue the second example, let's don't restart. The second example is going to be about using the code spectrum. So in this case, you have to import code spectrum instead of the conditional one. Okay, so you can either use a certain target spectrum to perform the selection, in this case, which you computed before, or you can compute the elastic design spectrum directly using the code. Okay, so here I'm going to set this as none, but you can comment to see how this works. If the target spectrum path is none, there's nothing, we are going to compute the elastic design spectrum. Elastic spectrum basically based on the given site properties, okay? So first, regardless of the selection, the building code, we are going to initialize our class or object, okay? So there are a few things that we want to set. Again, you can go to the tutorial to see what are all these parameters, okay? Here, I'm not going to go and explain all of them because it's actually very similar to what we have from conditional spectrum. But in addition to some limitations on conditional spectrum, you can actually set the number of records that you want to choose. You can set the number of records per event when you select the records. Okay, you are not going to select records more than 3 which belong to the same event. For example, if you use this option. Okay, this is another option that you can use in the code-based selection. If you are going to use, for example, Turkish building codes for your selection, And these are the site parameters that you have, and this is the related to the building. So you can use these options. If you already have the spectra, you do not need to define these, but you have to define the fundamental period of your structure, okay, which is 1 in this case. So based on this, based on the criteria in the building code, Turkish building codes, we are going to perform the selection and we are going to end up with this record set, okay? The same goes for ACE 716. You can again set the site parameters and get the target spectrum directly using the code EzGM. And then you have to define certain building building periods. Explanation for these are already, I think, given in building code, but also you can read, I think, from here. Yeah, from parameters, the descriptions are given here, for example. So this is a made-up example, so I don't do anything realistic here. Okay, I just have one single fundamental period in both directions, let's say, for my structure, and this is just one. Okay, I didn't define anything else, but the end result is going to be something like this. If you define something properly, it's going to be more realistic for your building. Okay, then you can have the selection also for the Eurocode. These are going to be the site parameters according to Eurocode, and this is going to be the fundamental period of your structures. Okay, then you'll end up something like this when you perform your gram motion record selection. Then the same way we did in the previous example, you can go on to select records, whichever you would like to choose. By the way, you have to uncomment. For example, if you are going to use only Turkish building codes for your selection, you do not need to do this, of course. So you have to delete this, obviously. And then upon performing the selection, you have to document, because here, each time I run some new selection, I change the selected records, okay? That is why you should be careful with that. So I don't want the records upon performing selection, and I write them into the files, into the txt files. Okay, this is the second example we have. So it just describes how to perform building code-based record selection. And if you go to the third example, it's actually, oops, let's go to the third one again. Oh, what happened here? Okay, I'm going to open it as before opening the third example. I'm just going to, okay, I think it's opened. Okay, let me show you. Because if you do not work on Binder, I think it just closes. So that's why you need to keep working on it. And I was not working, it was just idle. Okay, that's why it closed itself. So if you go to the third example, it shows you a framework where you want to carry out multiple stripe analysis to maybe derive rigidity curves for your structure upon carrying out probabilistic seismic concept analysis and performing condition spectrum based selection for your analysis. Okay, so this script basically is going to do a record selection, okay, for each return period that you define the segregation. Okay, let me show you, for example, an output, how it is going to be. I'm sorry, show you this. Yes. So the output is going to be something like this, right? You're going to have different return periods where you want to select gram motion records for, and for each return period, you're going to have the set of records and you're going to be a result of your selections, okay? Like 4.1, for example, probability of exceedance in 50 years. Yeah. This is going to be something like this. Okay. Basically, this example is going to describe how you can do this, okay? It is fully automated. You just need to change a couple of things, okay? So for that purpose, I just need to import a couple of things from utility module, and I need to import condition spectrum from selection module, okay? So first, we have an OpenQuake model, which is already there, okay? If you go to GitHub, we are going to actually run this OpenQuake model, okay? This is the OpenQuake model that we have. We are going to run probabilistic seismic hazard model analysis using this OpenQuake model. And we are going to then post-process the results of this. So the first step that you see in this cell is basically about running the hazard analysis and then reading the input file to post-process the results. Okay, so if you run this, as you see here, you are going to see some output like this. This is basically the output of OpenQuake engine. You see it runs the seismic hazard analysis. Okay, it gives you some information about your OpenQuake model, for example. I don't know, point source ruptures in your hazard analysis, area source ruptures that are going to happen in your analysis, and etc. Number of sources. So you see a bunch of outputs on the screen. This is basically related to OpenQuake engine, and in the end, the analysis is going to finish. And in this job ini file, I also, in addition to the seismic hazard analysis, I also compute the segregation of the seismic hazard, okay? Because I need this segregation of the seismic hazard also to define each scenario. So if I have the seismic desegregation and I have the computation of the hazard curve, I can post-process them with the functions that I have imported from from utility module. So for example, the hazard curve function just post-processes the PSHA results and shows you the hazard curve defined. I use RGZ as an intensity measure in this case. And the segregation MR is just going to show you the segregation results in terms of magnitude and distance. You see here. Then the third one is going to also include the epsilon for each beam that you have here. Okay, these are the epsilon values. So these can be quite handy to visualize the PSHA results that we have. All right. Then the third one, within this loop, we are going to select for each intensity measure type that you may have defined in the seismic hazard analysis, and for each intensity measure type and for each probability of exceedance that you have defined, or you may also say return periods, because you may convert it into a return period of each event. You're going to select ground motion sets with the same way that we have defined in the first example. Okay, this is basically the same step. These are basically the same steps, right? They're all the same. And in the end, you are going to select inside a for loop for each return periods ground motion sets, right? These are the ground motion sets that we have picked. Their spectra. We keep downloading them. We keep producing plots, and etc. We are going to do this 9 times in this example because we have defined 9 different return periods or probability of exceedance values inside the seismic desegregation. And in the end, we are going to finish our run, it takes around 6 minutes and 45 seconds, which is not that long if you think of the things that we have done in this example. Okay, so when you run this post-processing functions, I also want to show you what they are going to provide you. For example, these are the plots that you have seen. This is from another model. We're going to have something like this as a PNG file. We're going to have your hazard curve, sorry, and you have the values of those hazard curve. You are going to have intensity measure levels from your disaggregation. You are going to have mean distance values for each return period. You are going to have mean magnitude value for each scenario that you have, and also probability of exceedance in 50 years example for each each I don't know return period that you have. Okay, these are going to be just read from the uh, OpenQuake computation settings file. Okay, and for example, you can see the setting file from here. Right, this is going to be something like this. Okay, so for this, of course, you need to understand how OpenQuake works, and it should be related to some other tutorials where we talk about OpenQuake more, or you can also find some examples online. I think I'm not the best source to look for this. Okay, but anyways, there are some examples that I have already provided on my GitHub repository, and you can see that some of these hazard models are already available online, so you can retrieve them from the internet. And the final example shows you how to use the signal processing toolbox or the signal processing function class, whatever you call. It's actually called a module, but I keep mixing terms sometimes. So for this, we are going to import signal class, and we are going to import some of the functions. For example, there is one function to read motion record files from European database, read ESM. In this example, I'm going to work with these type of motions, and then you can use some other functions which are built in, which you can download. I'm sorry, not built in, which you can download from uh, Python package management systems. Okay, so in this example, what we do in the beginning is to read the record file that we have. Okay, basically, I'm going to read these record files, three components: the east, north, and up component. Okay, then using the read ESM file, I'm going to get acceleration values out of it. I'm going to check what is the time step. Okay. Then in the second step, I'm going to show you how to process those. For example, we can apply a baseline correction on each component. This is how we do it. The first parameter is the signal itself. The second one is the time step. The third one is the polynomial type that we want to use for the baseline correction. And if you want to perform, for example, filtering, in this case, I'm performing bandpass filtering. I need to have, again, the ground motion values of the signal. I need to have the time step. I need to define the cutoff frequencies. For bandpass, you have the lower and the upper bound for your frequencies, cutoff frequencies, and then you have to define the filter order because we are using Butterworth filter. This is the name of the function here. And then we need to define the type of the filter. Then this function shows you how to perform a linear elastic analysis of a single degree of freedom system. And finally, we can compute with the get parameters function many different intensity measure types, such as significant duration or also intensity or input energy and vice versa of these components, okay, or these signals. And finally, we can compute also ROT-D spectrum, ROT-D XX. And in this case, XX is the percentiles that we would like to compute the spectrum. Okay, so for this purpose, we need the first component, spectrum of the time history of the first component, and the recording of the second component. I said time history, but it should be the recording actually. And I'm going to use here the filter values, for example, to perform the computation. Then I'm going to plot some of the results that we have from this. Okay. By the way, I have to say that if you compute the intensity measures using getParameters function, they're going to be inside a dictionary which I call here param1 or parameters1, param2, param3. And again, you can find here what are these computed intensity measure types or seismological parameters. Okay, these are all the names that you can find, and you can use this keys to access your intensity measures. Let's go back. And if you plot those, you are going to see here, for example, the filter record versus the roll records. And then you're going to see the spectral acceleration values for the horizontal component 1, horizontal component 2, vertical component, and ROT 100, ROT 50, ROT 0, for example. So I believe this is all for the tool. I'm hoping all of this information that I just provide you guys are going to be useful for your future, and you can use it. I don't know. Please let me know if you find any bugs or if you want to discuss some ideas or if you actually want to improve it together with me. Just please let me know. And thank you for listening. Let's close it.